Now, boundaries, you have entire lines or curves check, that gets a little nasty. So once you find the critical points and any max or mins along the boundary, those are your candidates. And then you just have to sort out what's the max and min by evaluating all of them, evaluating the function in all of them, just plug them all in and see, well, the largest is the max, the smallest is the min. And we'll focus on the triangle with these vertices, 0, 0, 4, 0, 0, 3. We need to consider what's inside here and all three edges. So, first we do like before, check the gradient. What is the gradient? 2x minus 4, 6y minus 6. So we have one and only critical point. What is that going to be? 2, 1. Alright, now let's see where that point is. This is not completely to scale, but close enough. This is a critical point, 2, 1. It is in a triangle. If it was not in a triangle, we'd have to forget about it altogether and only check boundaries. But it is in a triangle, so that's our first candidate for where the absolute max or min might be. Now we have to check all the boundaries. So to do that, it's helpful to define the boundaries, in this case these three edges, using equations that relate x and y. So for instance, what would be an equation for the left edge of a triangle? X equals 0. Alright, down here?
Y equals 0.
Y equals 0. Now for here, it's a line, it's the equation of this line. If we start at 0, 3, we end at 4, 0, what's the slope of that line going to be? Minus 3/4, rise over
yeah.
x plus 3, so that's the equation of that line. So what we can do is, we can consider one edge at a time, plug in these relationships, which gives us a simpler function, what the function looks like along that edge, and then we're solving a single variable max or min problem. So for example, let's take x equals 0, put it in here. So f of 0 y is now going to be a function of only y. So it's going to be 3y squared minus 6y. So now we'll call this function g of y. So now we can just proceed as in a single variable case. G prime of y is 6y minus 6. So y is equal to 1. That's the one critical number along this edge. So when x is 0, y equals 1, that is a candidate. Equals 0. We now have function g of x, which is f of x, 0. So that's going to be x squared minus 4x. G prime of x is 2x minus 4. So x equals 2 is the one and only critical number for that, a function along that edge. So the point x is 2, y is 0 is a candidate. So we have this point and this point, so these three. Let's not forget these functions, these one variable functions are defined along closed intervals also. So all three vertices are candidates. We now have 1, 2, 3, 4, 5, 6 candidates because it's a polygon. So the vertices of a polygon are candidates. We have one more candidate to get. Anything that happens along this edge, well, there could be more than one, but this example is going to turn out to be one. So now we plug in y is equal to minus 3/4 x plus 3. So now we have a function g of x that's going to be a little more complicated before. We have x squared plus 3, and then we have this plugged in for y, squared minus 4x minus 6 minus 3/4 x plus 3. So now you have a function of x, you need to work with that mess and see if it has any critical numbers. I won't step through the entire differentiation now. But what happens is you get one critical number, x is equal to 104 over 43. So that is going to be somewhere around here. So we have 7 points, and y is 51 over 43. That is a candidate. So the one critical number critical point in the interior, the 3 vertices, and the 3 critical points we found along the edges. Those are where it could be the absolute maximum or minimum. All you can do is take these 7 points, plug them into the function, and see who the biggest winner and biggest loser. So what happens in this case, this vertex turns out to be the max's largest function value of 9, and then the absolute minimum is at this point. It's at -7. This one was pretty close to the min, but this function value is just a little bit lower. And there you have it. So notice we did not use a second derivative test at all. You don't need it. Check your critical points, and then critical points along each edge. If you have any vertices in the region you're working at, consider those too. So watch your endpoints. That's the main thing here. Even when you specialize to an edge, the edge has endpoints. That's why the vertices are included. Then you don't need a second derivative test. Just find any candidates, plug them into a function, and see who wins and who loses.